Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering 3 of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all 3 methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
Good day, everyone, and welcome to our webinar presentation. We'll be starting shortly here. Mano, I'm going to do just a last-minute mic check and make sure I'm coming through okay. Can you give me a thumbs up in the chat box if the audio is good? Awesome. Thank you, Paul. Oh, great participation. Great audience. Thank you, everyone. Mano Priya on our team is moderating today's session. She'll be helping us out in the chat box. She'll be dropping in some different excuse me, technical resources as we go through the presentation. I want to thank Mano Priya for her help in setting up today's event and share my appreciation for her efforts in pulling this together. My name is Adam Harris. I'm the CEO for C-Therm Technologies. This is a really exciting day for us. This webinar event we've been working on for a couple of months now. It's a really interesting collaboration with ThermoAnalytics. ThermoAnalytics is a leader in their field of developing thermal, fluid flow, and infrared modeling software. This really puts together a couple of really interesting pieces when it comes to tackling the challenge of thermal management in electric vehicles, and particularly in the motors and battery packs and so forth. What we're bringing from the C-Therm side here is the measurement capability to get really good data, really good representative thermal conductivity data, which is an excellent foundation to start from in putting the whole picture together. And really what ThermoAnalytics does is put that picture together with their modeling software. We've got a couple of experts joining us from both organizations, Dr. Zachary Adel, Senior Research Engineer with ThermoAnalytics, and Arya Hakimian from our C-Therm side, an application scientist with C-Therm. Today's webinar should run for approximately 1 hour. We're going to take you through some background information. We're going to talk a little bit about what thermal conductivity is, how you measure it, the different nuances of different types of sample formats, dealing with things like anisotropy or the orientation of the sample, for example. And then we're going to kind of go back and forth and talk a little bit about how that data gets introduced into some of the modeling and the significance from the modeling perspective. Understanding the difference in orientation, for example, can be very impactful ultimately in understanding what's really going on at a system level in terms of the thermal management. So I'm going to provide a little bit of the warm-up act here, but quickly transition you to our experts. Provide a little bit of background here on that expertise. We're very excited to have join us today. So as I mentioned, we have Dr. Zachary Adel. Want to just provide a little bit of background on Dr. Adel. He's a senior research engineer and feature owner for the TAITherm battery extension, a subject matter expert for vehicle electrification modeling, which we know is such an important area today in the world as we face the challenge of electrifying our vehicles and getting off of internal combustion engines, or ICEs. He has over 14 years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. He has worked with various OEMs and Tier 1 suppliers to model battery degradation with a focus on optimizing BMS control strategy. Dr. Adel received his PhD in mechanical engineering at Michigan Technological University in 2013. And really thrilled to have him with us today and share some of that experience and the significance of how it's brought forth in the TAITherm modeling software. From our side, we're going to be having Arya Hakimian, an application scientist with C-Therm Technologies. Arya graduated from the University of New Brunswick, one of Canada's top engineering schools. Subject matter expert in material thermal characterization, specializing in transient-based techniques, considerable R&D experience with experimental design, data analysis, process development. One of the things Arya is going to be talking a lot about today is the importance of method selection, because that's really where it starts in terms of getting good thermal conductivity data. So understanding the different nuances to measuring in an isotropic material versus a liquid versus other types of material formats. So I think it should be a great session, and really pleased. This was our most popular webinar this year, just based on the registration. It really shows, I think, a keen interest out there in the industry. This is a challenge that many of us are trying to face, and there's considerable time pressure in terms of getting product to market in a robust manner, dealing with the performance issues, the thermal degradation, thermal runaway potential in these scenarios. So really great to have organizations collaborating together, such as C-Therm and ThermoAnalytics. A little bit of quick background on who C-Therm Technologies is. Zach's gonna, I think, provide a little bit further intro on ThermoAnalytics a little bit later. But some of you are, I think, very familiar with this, just judging by the participants list. Some of you might not be as familiar with this. So our purpose in life, our raison d'etre, is to simplify thermal conductivity testing, largely for the materials of tomorrow. So we help support a lot of organizations in the development of new materials, novel composites, formulation development, and also in the material selection and quantification of performance claims, all centered around making thermal conductivity simpler to measure, offering an ability to test under really truly representative conditions. A lot of traditional methods for thermal conductivity present significant biases in terms of really representing, in contrast, the application environment. So, whether our sensors are applied in thermal chambers and nuclear irradiated hot boxes, humidity chambers, under high pressure conditions with some of our high pressure cells. What we really advocate in this space is the importance of testing representative conditions and making thermal conductivity more accessible and simpler to measure. So you'll see on social media our hashtag simplifying thermal conductivity. If you're on LinkedIn or Twitter, if you click that hashtag, it'll give you a nice list of different resource materials, different references from different posts over the years. The instrument we're going to be referring to a lot today is called Trident. Trident is significant in bringing together three of the most prominent, powerful transient methods for thermal conductivity. And we really focus on the transient class of sensors because they're faster, they're more versatile, they're more precise, they give you a better flexibility and better ability to test truly representative samples. But there's not a silver bullet in those three methods. Each of them has their benefits and their limitations. And we'll try to speak a bit to that today. But something that's really a great resource is the method selection guide that has been authored by a group of experts, some from C-Therm and outside collaborators, and really understanding the points of difference of these different methods. But in a quick high-level description, the MTPS is the simplest one to operate. It's the single-sided sensor, the stainless steel object you see to the lower right of the Trident product. Trident was launched new in end of 2019, represents several $1 million in multiple years of development efforts. The MTPS is the most novel of the sensors. It really empowers unique capabilities and simplifies a great deal the measurement of thermal conductivity. Tests solids, liquids, powders, paste. Very versatile sensor. The one in the middle is our needle probe, a transient line source. This is very robust, sheathed in stainless steel, excellent for dealing with very sticky materials. If you think, for example, of testing a polymer melt, this is a great way to do it. And we just launched a new high temperature version of this, which is really purpose engineered for plastic injection molding, being able to handle very high temperatures up to 300 degrees C and very high pressures, representing the application conditions in plastic injection molding. So if you're involved in the polymer sector and you're looking for the most advanced capability for polymer melts, there's a new offering just launched this past month. To the left of that is the Flex transient plane source sensor, and we call it Flex because it's a flexible sensor. It's a nickel foil. It's encapsulated in a polyamide material. So it's sandwiched on both sides of the nickel sensor. And then that sensor is placed in between two sample material. Flex, so flexible in terms of the sample format, the form factor, but also flex in terms of giving the user more flexibility and control over the experimental parameters. So in this method, and it is a method really oriented more towards a higher level of expertise on the user side, it gives you more control over the regression analysis. You can alter timing and power parameters. You have different sensor size options, and there is an iterative step progression through the regression analysis and determining activity. This unlocks some really advanced features in measuring thermal conductivity. And I'll talk in a minute a little bit about some advanced utilities available on the Flex TPS. I love this quote from Abraham Maslow. It really captures the value proposition to Trident. When we talk about thermal conductivity, and you can scan all available methods from guarded hot plate, heat flow meters, laser flash, all these different types of techniques. There's lots of good ways to measure thermal conductivity, but a lot of them have very specific purpose-oriented applications of them. And so it's really important when we're measuring thermal conductivity, we get our method selection correct. A lot of the mistakes we see made in published results of thermal conductivity, of erroneous data, and you can just imagine how that then propagates into thermal modeling. A lot of those mistakes are made from applying a tool it was never meant to be applied on. So, you know, this quote from Maslow, I think, really kind of captures the essence of that, that when all you have is a hammer, everything looks like a nail. So it's really important to take more of a toolbox approach when it comes to measuring thermal conductivity, have some different options available as represented with Trident and having those three different methods. And then with the Flex TPS, I just wanted to also mention, because it'll be referenced, I think, in some of Aria's work. There are some special utilities additionally available for different sample formats. So there's a slab utility. This is really useful for testing very high thermal conductivity materials. So if you think of like copper sheets or highly conductive metals, slab is a very valuable utility. It greatly reduces the sample thickness requirement. You'll input the thickness requirement with the slab utility. That's not typical with the operation of these transient methods. It's unique really to the slab utility where you input the thickness and you're actually penetrating the full boundary on the sample. But this allows for testing a very effective solution for measuring high conductivity material. Anisotropy deals with orientation. So if you can think of a polymer that has glass fibers that are structured in an in-plane direction, the in-plane thermal conductivity is going to be different than the through-plane thermal conductivity. So you want to really be able to distinguish that heat transfer, and I think there's some interesting modeling that speaks to that significance. And then, of course, we're seeing a lot of thin films applied in different areas of applications, in electronics and batteries areas, the touch screens in the vehicles. Thin films are something that is really important to be able to measure well. So some good options there. So I mentioned this guide available for method selection. I think earlier in the discussion in the chat box, Mano has dropped that link in. This is a pretty comprehensive free resource. I think it's over 50 pages, and it really takes you through what is thermal conductivity, what's the difference between steady state methods and transient methods. Talks about all the different techniques that are commercially available, the ASTM standards associated with them, and what applications they're really meant for. So it's a great way of mapping your materials and application to the specific tool set that's best designed for the characterization of those materials. I'll end with a short testimonial, and there's a nice webpage dedicated to collecting our client experiences. We have all kinds of interesting references there from groups like 3M, NASA, Honeywell, Intel, all kinds of different clients of C-Therm around the world. This is just one we've selected in this case from Covestro, Jose Fonseca, speaking on the C-Therm instrumentation, providing his group a fast, accurate capability to measure thermal conductivity of polymers with the patented high-precision MTPS sensor. Comments on how popular it's become within his group, the quick, easy, reliable measurement, and the general support provided by C-Therm. That's a fairly typical customer experience. If you'd like to check out some others, I think Mano is dropping in a link to that page of where that is available. I see Arya has joined me on screen. Welcome, Arya. Arya is a member of our and I'm very pleased to pass the baton on to him. He always does a great job curating this material, this content, and really illuminating areas, sharing his expertise in how to measure thermal conductivity. So at this point, I'll pass this over to Arya, and I'll be rejoining you later in the presentation.
Awesome. Thanks, Adam. Hello, everyone. As Adam mentioned, I'll be doing a little bit of some background on the measurement side with respect to the thermal conductivity characterization before we kind of get into some of the simulation work that Zach will be presenting here shortly. So before we get into it, again, the main reason behind the importance of this type of investigation with respect to thermal management, you kind of tying back into the different failures that can occur with these, in this instance, electric vehicles. Different news articles have popped up over the past, few years, kind of see these, fires and thermal runaway events that are occurring. And in fact, there is some data showing that the temperature factor can account for about 42% of many of the faults that are occurring in these electronic components. Of course, there are other factors, seeing here mentioning vibration, so different mechanical influences, as well as humidity, but, temperature being one of the most important. So with that in mind, really this is coming down to the thermal conductivity, the ability of these different materials to dissipate that generated heat. So before we go into this very further, just a very high level background. What is thermal conductivity? Well, it's essentially defining the rate of heat flow through a material. You can see if we break down the units of thermal conductivity, which are watts per meter Kelvin. Watts are coming from the thermal input, that thermal energy that is being introduced into the material. This heat is then traveling across a given thickness, denoted here in meters, and of course across a temperature differential denoted in K. So obviously thermal conductivity, somewhat simple in this approach, but obviously can get very complex once you get into the nitty-gritty of it all. And really, when we're talking about thermal conductivity, there are a lot of factors that influence material performance. One of the main ones is generally the state of the material, so whether it's a solid, a liquid, powder. These, even if it's the same material, just at different temperature states, this can have a large influence on the thermal performance. The structure, composition, density, all of these factors come into play. And they're important to understand when you're looking to do this type of characterization. As Adam alluded to earlier, representative testing is really important because as you change certain variables, this can have a compounding effect on the resulting thermal conductivity. Tying this into electric vehicles, see just this image on screen, there are a lot of different materials involved here. Whether you're looking at the different components of the chassis, the axle, the batteries themselves, the different electronic components. You can be dealing with metals, polymers, ceramics, liquids. So of course, this is a very complex system when you're looking to quantify it and do these types of analyses. So it's really important to have the best tools in your kit to handle the different types of samples. Now, for us here today, the main thing we'll be taking a look at is specifically the different types of polymer-based materials. A lot of those are, incorporated into the battery packs, the electronic components as well. So understanding how heat transfers within a polymer, you can see just in this kind of high-level example, the thermal conductivity. You can relate this to the volumetric heat capacity, the rate at which the speed will travel within a material, and also the available free path length for the phonons to travel. The mean free path really is going to be a property that really dictates how well that heat will transfer in a material. The larger that is, generally the higher the effective thermal conductivity will be, as there's less scattering involved, less resistance to that heat transfer within the bulk material that is of interest. Now, of course, depending on the type of material you're working with, how it was produced, there can be different levels of organization within the matrix itself, and this will have a resulting influence on the thermal conductivity, again, based on that available free path length. So as you get into a more organized structure, this will generally result in more crystalline matrix, resulting in a higher effective thermal conductivity. So now, of course, there are different ways that this can be accomplished to get at these more pristine or more ideal structures. Ways of increasing the thermal performance, again, better organization within the material. However, many times, and a lot of what we're seeing recently, is by introducing a conductive filler, an additive material, whether that's a carbon-based filler, a metal nanoparticle, what have you. Generally, a higher load of that filler material will result in an increase in the thermal conductivity performance of that sample. On top of that, though, there's also notes that the aspect ratio of the filler itself will also have an influence. So higher aspect ratios, even within a same filler type, will have a different net result on the thermal conductivity increase as well. So there are a lot of different factors at play here, but of course, when we're trying to push the limits and get to these more novel structures, more novel materials, these are a few of the things that can be adjusted along the way to get at those desired properties. When we're dealing with these types of modifications, though, this is where you can get into some different material behavior. I know Zach will be discussing some of this in his coming slides, but anisotropy, or a material that's anisotropic in nature, is one that has these directionally dependent properties. These types of samples we're seeing more and more come up as call it an area of interest for many researchers. It does require a more complex test method. It's not so straightforward as some of the more, call them simpler materials to test. But at the end of the day, these directionally dependent properties may be desirable. You're really looking to fine tune the heat transfer along the surface of a material compared to the through plane or through the thickness of the sample. So these different resulting performances of these materials can be beneficial and designed in a way to really get at the most optimal performance of the system that you're looking to create. So that being said, I will come back in a few minutes to discuss some different test methodologies, but next I would like to introduce Zach from ThermoAnalytics, who will take us through a little bit on some of the simulation work that was done. So I'll leave you with that.
Okay, thanks, Arya. As Adam mentioned earlier, I work for ThermoAnalytics, and we're a leading developer of thermal fluid flow and infrared modeling software. We have a global client base, and we offer software and services to solve challenging thermal problems. We have three main software applications that we develop and sell. The flagship software is TAITherm, which is a thermal simulation software. We also have Musis, which is basically TAITherm plus some infrared capabilities where you can simulate infrared signatures. And then we have CoTherm, which is a process automation software, and it's commonly used for coupling different models in different software suites. We have several extensions available. We have a battery extension, a human thermal extension, which predicts comfort. We have an exhaust extension and a drive cycle extension for coupling with CFD. TAITherm is a thermal simulation software with a few unique selling points that makes it very useful when it comes to designing vehicles. It is a transient solver. It's very fast, so you get results in hours or days instead of weeks. It's accurate, considers all modes of heat transfer, and it's user-friendly. And we also have very good customer service and experience at the company in solving thermal problems. So I have prepared 2 case studies today that involve modeling in electric vehicles with looking at different thermal conductivities and types of conductivity. The first one is an electric motor, and there are 2 components in the motor that are temperature sensitive. One is the insulating or potting material. It can handle temperatures between 90 to 240 degrees Celsius, depending on what it's made of. And then for permanent magnet synchronous motors, the magnets are also a component that's temperature sensitive, and that can handle 150 to 180 degrees Celsius. And you can see here on this graph that some of the most important considerations are looking at the expected life hours of the motor and how the total winding temperature determines how long the motor will last. And as an example of the types of problems that engineers face, continuous power is typically limited to about 50% of peak power, and that's due to thermal limits. So designing a better thermal management system or a better motor with different materials can really increase the amount of power that you can get out of them. This is a TAITherm model that we set up to illustrate the effects of thermal conductivity on motor performance. It has 1.8 million elements in it. It is a combination of solid parts and shell element parts. The solid parts are the main ones that we'll be looking at. That includes the stator iron, stator windings, potting compound, and rotor. And then it has uniform jacket cooling and axial cooling between the stator teeth. These are results for different potting compound thermal conductivities. So they range anywhere from 0.2 watts per meter Kelvin to 1.87 watts per meter Kelvin. I think I've got the units a little wrong here. It says meters squared, but that's a meters Kelvin. And so we can see by increasing the thermal conductivity of the potting compound, we can reduce coil temperatures by about 35 degrees Celsius. And when we're looking at the temperature of the rotor versus thermal conductivity, we can identify a point on that graph that corresponds to the temperature limit. And what we see is that the thermal conductivity should be about 0.7 watts per meter squared Kelvin to meet lifetime requirements. You can also look at the forecasted lifetime in expected life hours versus the thermal conductivity of the potting compound. And in that case, you can see what happens if you want to extend the life of your motor or operate it at higher powers and still get acceptable lifetime. The second case study that we've prepared is on thermal runaway, and we use the NREL thermal runaway model, which was derived by the National Renewable Energy Laboratory. It describes heating from unwanted chemical reactions at elevated temperatures. It has temperature-dependent reaction kinetics and is used to evaluate the risk of cell-to-cell propagation of failure to avoid cell-to-cell propagation of runaway. The thermal runaway model is a set of empirical equations that are fit to test data. They include the volumetric heat rate, which is a function of heat of reaction, battery composition, rate of reaction, and temperature-dependent rate constants. And for the case study that we've prepared here, this is a stack up of 6 different cells with carbon fiber heat spreaders between the cells. And it's important to have some kind of strategy to mitigate thermal runaway in this case, to make sure that occupants are safe. Typically, the standard is that the time between a thermal runaway warning sign appears in a car and the amount of time that the occupants have to get out of the car should be 5 minutes or greater. So to mitigate thermal runaway, sometimes people use anisotropic heat spreaders between the cells. And what that does is basically eliminate the highest temperature of the hot spots from going directly to the neighboring cell by spreading that heat out along the entire surface, and with low through plane conductivity, reducing the heat transfer between cells. So the first case that we looked at was the anisotropic case, which is the most realistic. And this is including the thermal conductivities as measured by C-Therm for some characteristic carbon fiber cases or materials. And what we see here is for the anisotropic heat spreaders, the thermal runaway actually propagates from the trigger cell to the adjacent cell, but doesn't propagate further through the pack. So we have 2 cells in this case going into runaway, followed by a cool down period. If we were to simplify this and just look at isotropic thermal conductivity, this could greatly affect the prediction that we get, and that could also be an important safety factor for the design of vehicles. So in this case, we've taken a common thermal conductivity value of 1.2 watts per meter Kelvin. And what we see when we simplify this heat spreader material properties is that the thermal runaway is predicted to propagate through the entire pack. And that's not really realistic compared to the more accurate case. So we looked at another case of isotropic thermal conductivity, which was the average of the in-plane and through-plane conductivities. So this is 1.65 watts per meter Kelvin. And when we increase the conductivity, such as this, in this case, the first cell runs away, followed by a cool down period. So this predicts that we have less thermal runaway propagation, and that could be dangerous, particularly when you're looking at cases with more cells and higher heat rates, or possibly more energy dense compositions inside the battery. You don't want to predict a safer situation than you would expect to see in a vehicle. So these are just some cases where we've looked at the impact of thermal conductivity and how different scenarios can be very sensitive to that thermal conductivity. So now I'll hand it back over to Arya to talk more about the measurement capabilities of C-Therm.
Awesome. Thank you very much, Zach. So yeah, what I'll be kind of discussing up next is really just essentially how to best quantify the thermal conductivity. Of course, Zach kind of demonstrated some results on a few different types of materials with ranging thermal properties. But as was mentioned earlier, really the best instrument or the best tool for the job can sometimes vary depending on the type of sample that you're working with, perhaps the size that you have to measure, and things like this. So I'll be discussing 2 different methods with a couple different examples here today. First being the MTPS modified transient plane source. Again, this is a single-sided sensor. Does have a guard ring measurement directionality, so you do get a directionally dependent measurement with it, which conforms to the ASTM D7984 standard. As well, we will all be taking a look at some case studies with the TPS, the more traditional flex transient plane source. This is, of course, the double-sided sensor. We'll be highlighting the specialized anisotropic utility. Again, this is how we did some of those measurements for the simulation studies that were just discussed. And this method operates in accordance to the ISO 22007-2 standard. So just to give a principles of operation, so kind of the high-level overview here with the MTPS, how the sensor works is there's a known amount of current which is applied to the sensor's spiral heating element, and this results in a small amount of heat being generated at that sample sensor interface. Essentially what is going on here is the sensor is simultaneously monitoring that change in temperature that occurs as a function of time. And the rate of change is what's used to get at the different thermal properties of the material. So in a very kind of simple example, you could see something like a foam, something lower in conductivity, more insulative in nature, would experience a much steeper rise in temperature, whereas something more conductive like a metal would be much flatter. With the MTPS, again, it's very important to note that related to the guard ring, which surrounds the sensor coil, this helps support a one-dimensional heat transfer into your sample. So again, certain measurements provide you with average values, others are directly in plane versus through plane. With the MTPS, you are getting that directionally dependent measurement based on the sensor and the sample position. With the MTPS, one of the reasons why it is one of the more simpler, easier methods to use, also one of the fastest, it is related to the fact it is factory calibrated. So depending on the type of material that you're working with, there's a specific calibration that's preloaded into the system. So it avoids users having to go around and play with your time and power settings. It really is much more of a plug and play solution for a lot of groups that we support in this type of industry. With the MTPS, you can see it on the right there, that green portion of the chip, that is the active area of the sensor, and that measures about 18 millimeters in diameter. So as long as you're able to cover that very small active area, you're essentially able to take a measurement. This can be really helpful when you're dealing with limited sample sizes. The example on the right are these, you can see these kind of tensile bars. Being able to take measurements in both the through plane and the in plane direction are possible, again, simply by how you're orienting the material on top of the sensor. And again, in this example here, we can see that there is, quite a noted difference in the thermal conductivity along the different directions. One of the big things we've seen a lot of groups take advantage of with the MTPS is the aspect of thermal mapping. So surface mapping or thermal mapping, this can be used to assess dispersion of a filler material along the face of a sample. So again, if you're adding a conductive filler into the polymer matrix in an attempt to increase or simply modify the thermal properties, making sure that you're getting even dispersion is going to be very important. Issues such as agglomeration or settling can really result in some non-ideal performances within the matrix of the sample. Of course, you may get heat dispersion issues, localized hotspots, and things like this. So again, with the MTPS, has about an 18 millimeter active area. You're able to place that along different surfaces and essentially map out the thermal properties of that material. The example taking a look at here today is this, it's a very kind of simple example, but it was an epoxy resin that was cured with a conductive metal nanoparticle dispersed in the matrix. This was done in a wide mold to really increase the overall surface area, and very visibly right out of the gate. You can look at that image on the right there and see some quite non-uniform dispersion. However, we're going to use this example to just illustrate how the effective thermal conductivity measurements that are taken across that surface can be used in this instance to correlate to the filler concentration, where a higher effective conductivity value will be indicative of a more filler in that specific location. So how this is done, again, it's just simply moving the sample across the surface of the sensor, so having different test locations across the material, and then taking those measurements and determining if the dispersion is uniform or not. So if this was an evenly dispersed sample, you would expect location 1, 7, 6, all the different test spots to be essentially the same. However, in this particular example, what you'll notice is some quite large variation across the sample surface. In the upper left corner, indicative of that spot number 2 there, you have a very low effective conductivity measurement coming in at about 0.347. Whereas to the right of the image there, where you get more of that concentrated buildup of the filler on the backside, coming in at an effective conductivity value almost 3 times larger. So in this example, very clear to see that the dispersion is not uniform. However, if you're dealing with a sample that may not be so visibly detectable, maybe you're dealing with an opaque sample, maybe the filler is the same color, or it's non-transparent, you're not able to see through it, then of course the MTPS can be used in this fashion to determine these filler dispersion issues that may be present. And again, very important when you're dealing with formulation development, looking to get those thermal conductivity values to the regions and the zones that you're looking for. So to pivot into the TPS, or the transient plane source method, again, just a high-level overview on the principles of operation. Right out of the gate, you'll notice the biggest difference in your test setup is that it's a double-sided sensor. So of course, we need to have 2 samples in contact, one on top and one on the bottom. These samples are assumed to be identical in nature, and this is where the combination of the 2 sensors can come into play. Of course, if you had dispersion issues with the filler in kind of the showing in that previous example, then that type of material may not be really appropriate for testing on the TPS method. However, once you've kind of optimized the samples and you know your dispersion is uniform, you're not getting any buildups, then of course you can bring it into further verification and validation with this method here. The TPS inherently is somewhat more complex to operate. Unlike the MTPS, which is again more of the simple plug and play with the various user calibrations preloaded, TPS requires you to manually adjust the time and power settings for your measurement. You also have access to some different sensor sizes as well. So you do have a lot more control and customization over your measurement. Now, at the end of the day, we're still essentially monitoring the change in thermal response, or that change in temperature that occurs over time. This will be true for any of the transient class of thermal characterization techniques. But with the TPS, because you have this freedom of control with your test setup, at the end, there is a validation process that you have to go through in order to determine if the settings that you used for your test are in fact valid. Now, all these checks is coming with guidance provided by the ISO standard. Really gives you the detailed requirements for how you go about doing this test properly, and the different requirements that need to be met. And with the TPS, one of the other benefits is that you do have access to more of these advanced utilities, and the one that's of interest for us here today is the anisotropic utility. So of course, this is for testing of materials that would have a different in-plane versus through-plane thermal conductivity. We'll note that it is limited to orthotropic materials. So those are samples that in the in-plane direction, so in the radial direction here, the XY, it is the same. So there is no difference along that range. Some certain materials that are fully anisotropic or would be completely different in the X, Y, and Z direction do require some additional considerations for valid testing. With the anisotropic utility on TPS, another note, it does require the manual input of specific heat capacity as well as the density of the material. So this is inputted directly into the software. This is somewhat similar to those who may be familiar with laser flash techniques, where essentially the density and heat capacity are required as that direct input for all of your measurements to get conductivity. When you're operating with this specialized utility, you'll see a similar requirement there. But again, a really strong and powerful tool for assessing anisotropic behavior within a material. So just a few examples and some data that was collected here. We can see some more simple examples with the TPS testing of some polymer materials. Thermal conductivity results here are noted compared to some literature or reference values. And you can see that in some cases, the difference between the in and through plane conductivities can be fairly minimal. The example on the left, while there is a significant difference, albeit not to the extreme levels as perhaps the example on the right, where you're getting very, very large differences in those in-plane and through-plane thermal properties. Now, of course, sometimes these behaviors and these specific thermal properties are desirable. You really want to have a large difference, as Zach alluded to in some instances reduce those thermal runaway events. But again, being able to quantify the level of anisotropy in the material and do that accurately and repeatably are going to be very important here to get those called the ideal inputs for some of those types of simulation studies. Here we're showing some just another test set on some composite materials, again tested with the TPS method. And again, in this example, we can see about an 88% difference between the in-plane and through-plane thermal performance. So again, depending on the type of material that you're working with, if you were assuming that the average value here was representative of the bulk, you can really be biasing yourself and setting yourself up for failure, when in fact you can have some very large differences in thermal performance in these different directions within a singular material. So just in conclusion here, from a thermal measurement side of things, of course, thermal conductivity, a very powerful metric to be used in the quantification of thermal management. In this example here today, focusing on electric vehicles, but of course, in any application where thermal is going to be an important consideration. And as well, the combination of the MTPS and TPS can really be used in tandem here to cover a full range of sample types, formats, sizes, and things like this. From the simulation data that was presented by Zach, of course, noting that significant differences in temperature can be noted in this example for the coil temperature reduced by 35 degrees Celsius with the varying thermal conductivities of the potting compound, ultimately leading to differences in the motor power output. So being able to increase that metric is going to be very important for the advancements of these types of products in the coming years. And as well, again, the really important aspect of the battery thermal runaway modeling, noted to be very highly dependent on those thermal barriers. Again, highlighting the aspect that isotropic behaviors may lead to inaccurate real-world conditions. So the ability to understand the anisotropic aspect to some of these materials can be very important, especially for the simulation side of things. And again, the higher performance, lifetime, and safety noted with the dual approach. So the thermal conductivity estimation, as well as the 3D prediction modeling. So with that, I would just like to take some time from myself and speaking for everyone on the webinar here today. Thank you for your attendance. As we kind of go into the conclusions here, did just wanted to have a few last notes. So there are various additional resources available on our website, www.ctherm.com. Previous webinar recordings are available there, as well as a tech library with a range of different application notes, case highlights that may be of interest to your field. If you were interested in taking a next step, I believe some of these links are being inputted into the chat box as we speak, but booking a virtual demo, taking a call, looking to get a quote, happy to assist there if needed. And as well from C-Therm side, we do have some upcoming webinars may be of interest. One coming up on the 25th, the performance characterization of novel construction materials with a focus on accelerated thermal conductivity methods. We have one in the following week in December. This will be another guest focused webinar group for CoolMag. We'll be discussing enhancing and testing the thermal conductivity of potting compounds for power electronics, somewhat related to some of the aspects that were discussed here today. And then the following week, December 9th, our recent advancements in thermal conductivity materials and filled systems. So if you were interested in any of those, the registration is live. And a note from ThermoAnalytics, just wanted to plug, there is an upcoming user group meeting, which is live for register right now. This will be held on Tuesday, March 22nd through March 24th of the coming year. And again, all of these links are being posted in the chat as we go along here. So all that being said, I would like to conclude again saying thank you and inviting everyone back on for the Q&A session.
Awesome. Thank you very much, Arya and Zach. A wonderful presentation. This was really great and a wonderful experience collaborating with ThermoAnalytics. So Zach, a big thank you to your group for put this together and really strong contributions. At this point, what we'll do is we'll stop the recording. We're going to pivot now to the Q&A session. For anyone that's dropping off or viewing this as a recording, I'll echo Arya's sentiments and say thank you very much. Appreciate your time and hope you found it an interesting session, and we certainly hope to continue the discussion. Okay, so we'll stop the recording here and we'll bring up the Q&A.